Welcome to the Databricks Skill Builder series. We're glad you're here.
Well, thank you for joining this skill builder session. My name is TJ Cycyota. I'm a specialist solutions architect at Databricks, and I will be covering a use case that we helped a customer with around bin packing. So just a quick overview of the agenda. I'll spend about 10 minutes going through a blog post that covers the problem we're trying to solve, go through a little bit of the technology, Ray on Spark, and just the Ray library in general. And then we'll spend about the bulk of the time going through the code. All of the code we're going through is public. It's part of a Databricks Solutions Accelerator. So you can go through it at your own pace. It should be runnable in any Databricks workspace that you have access to, and you can modify it as needed. So to kick things off, I'll go a little bit into the use case of the problem that we were trying to solve. So we called the blog Thinking Inside the Box, How to Solve the Bin Packing Problem with Ray. And really, this is a classic optimization problem. So if you've ever moved houses or apartments, you've experienced this. You've had to put things in boxes. And the challenge you're trying to solve is how many boxes do you need? What's the optimal way to put your dishes and your plates and your mugs into a box so that there's not a lot of empty space, but there's no box that's too heavy. You don't need all these tiny little small boxes. And this is essentially many companies around the world solve hundreds of, or if not thousands of times a day. So it's pervasive across real world applications. And there's a lot of different ways to solve this problem. Databricks was working with a very large industrial equipment manufacturer who was solving a variation of this problem for their supply chain. So their real use case is they sent containers to their vendors. So their vendors manufacture parts. Those parts get sent in the containers to a centralized manufacturing plant. And the company that Databricks was working with is trying to figure out essentially what box do we send to which vendor for the parts that they're going to manufacture. And it's tricky because you can't just send every vendor a giant shipping container because then your factory is filled with all these shipping containers, whether or not you use that part one time a day or 1,000 times a day. But you don't want to send too small of a box because that means you have to replace that container on the factory floor at multiple times a shift, which is just inefficient. So there's a kind of a sweet spot per part, depending on how many times it's going to be used in a manufacturing shift. Um, to make sure that you send the right size container to the vendor that's producing that part. So again, in a really summary sense, we're trying to avoid wasted space in containers, but also making sure we're sending the right size of container to the vendor to optimize the layout of the factory floor. So the first part of this problem is actually the bin packing problem. So if we kind of break this problem down into the kind of logical steps that we would need to solve, our first place we start is a bill of materials, the items that we're going to use in our factory. So we basically need to think through every item in our bill of materials and figure out what is the optimal container for it. We also have, because we as the manufacturer send the container to the vendor, we have different container size. So this could be, a couple. You can think of like a small milk carton to a giant shipping container. We have a lot of options of the size of the container that we send. And really importantly, if you think about the way that you could put a rectangular prism or a box inside of another box, there's essentially 6 different starting orientations with which you can put that first item. So the end efficiency is very sensitive to the starting orientation. So we have to kind of permute all of those options as well. So what does this actually look like in a computing sense, right? We're trying to optimize this process. So what if we were going to use it on single node Python, right? Truly run the pseudocode as is with a series of nested for loops. So if we have millions of iterations, and really millions of iterations is pretty easy to get to. If we have 20,000 items in our bill of materials, 20 different container sizes, and then the 6 starting orientations, that's easily 2.4 million combinations of things to model. It could take hundreds of hours to compute, right? So just a simple naive implementation in Python, it might take nearly a month to run the simulation. So it's completely untenable. This is too slow for real business processes. So we want to figure out how to optimize this modeling process. So this brings us to Ray. So what is Ray? Ray is a very popular parallelism framework that's available on Spark. It runs really well on Databricks. So the one way to think about Ray is Spark is used for data parallelism. So we have, a billion rows of data and we want to calculate the average of a certain column in there. With Ray, we can think of it as this logical parallelism library. So we have one row of data, and we want to compute a million permutations on it. So it's essentially what we're trying to do here, right? Few inputs. We want to run a bunch of simulations on those inputs. And you can use it for a lot of different things. I'll just highlight Ray for ML infrastructure. There's a lot of different use case Ray supports. All of this runs perfectly well on top of Databricks. In this example in the code, we're just using Ray core. You can kind of see that all of the other application-specific libraries are built on top of Ray core. So having a really intuitive understanding of Ray core is a great place to start. And this bin packing example just uses Ray core, none of these other higher level abstractions. So how do we model this? Kind of shown graphically, we're going to start with those 6 starting orientations at the lowest level, and we're going to pack those inside of a bin. And I'll show the library we use in Python to do that. Then we're going to do that bin packing for each of our containers. So you can see here we have these 9 containers listed. We're going to run those 6 simulations for each of those starting containers. And then again, each of these containers is possible for each of the parts, so we need to run this one time per part. So the way we do this in Ray is pretty simple. We just build our basic Python logic, and then we wrap it in these Ray decorators, which is kind of a Python syntax we can use to take any arbitrary function or class in Python and make it compatible with Ray's distribution methods. And we'll go through this in a lot more detail. This is kind of just a summary. And at the end, what this really means is this customer was able to scale up their modeling process by 40x. So, instead of taking 27 days, it took 1/40th of that time. It also scales linearly. So because we can distribute and parallelize this process, if we wanted to run faster, we just throw more compute at the problem, right? So instead of 20,000 items, if we had 40,000 items, we can just double the size of the cluster to get it to run in the exact same amount of time. And most importantly for this customer, they had actually attempted to solve this with some native Python primitives like parallel processing libraries and async. So with Ray, it dramatically simplified their code base. So at the beginning, they just had essentially one PhD level data scientist who could understand what was actually happening in this modeling process. And by converting it to Ray, it drastically simplified the code and made it so other people could apply these techniques to new use cases to kind of scale the impact of this optimized bin packing. So with that, this brings us to the solution accelerator. If you want to do a quick online search, it's just called Scientific Computing Ray on Spark. This is a public GitHub. It's part of the Databricks Industry Solutions. We hope to extend this with other kind of scientific computing, things like traveling salesman problems, other optimization and simulation applications. For now, it just includes this bin packing optimization examples. So we'll go through these 3 examples in the next few minutes. So to get started, I imported the notebooks as a Databricks Git folder, and then I associated with a cluster running the Databricks runtime 15.3, and it's the machine learning version. So in the newer MLRs, machine learning runtimes on Databricks, Ray comes prepackaged. You don't need to install anything. So it just works out of the box. And there's newer runtimes in 15.3, but all of the newer ones should include Ray as well. So I've just downloaded the notebooks and associated it with this cluster. Now let's go through a little bit of the high-level logic we're going to use. So the first thing is we're using a library called Py3DP, which stands for Python 3D bin packing. So it's an open source implementation of a bin packing methodology. And it's really kind of simple to understand. So we have essentially a single node Python function. We're not using Ray yet. In this function, we're going to take in a set of arguments. These arguments are going to be a tuple containing the item and the bin dimensions, right? We want to pack the item into the bin in a certain starting orientation. So all we're doing here is doing a little bit of logic. So if the item is too big or too heavy for the bin we're trying to pack it in, we just say 0 will fit. And then if some items will fit, we run this packer class that the Python 3D bin packing library implements. We won't go into all the details. It's a very well-documented library, very simple to use for this problem. But this function will just return the maximum quantity of that part in that orientation in that bin that we're using, and then the fill rate, which is just a percentage that shows how full is the bin with that starting orientation. So for example, we can take a really kind of simple example to start. So let's say we have a bin. The X, Y, and Z dimensions are 10 by 5 by 2, right? So 10 times 5 is 50, times 2 is 100. So this has a theoretical volume of 100 units. Doesn't really matter what a unit is. And we want to put an item in it that's 1 by 1 by 1, right? So it's 1 unit by 1 unit by 1 unit, should fit 100 of these inside our bin. Really importantly, the weight is 1, which is, 100 is less than 1,000, which is the maximum weight capacity of our bin. So if we run that simple function, again, not using Ray yet, we say that this has 100 fit items and our fill rate is 100%. There's no empty space in this bin. So we can run this a couple more times with an odd size container. So now we have, the Y dimension of the item is not a divisor of the bin Y dimension. So we're not going to get a full 100% fill rate. Looks like in this case, we can get an 80% fill rate and there's 40 items that can fit in here. So hopefully this very simple, everyone's done this in real life, which makes this use case really fun to talk about. Everyone's tried to put things in a box and sometimes it didn't fit. You needed a larger box or you couldn't get that box 100% full. That's all we're doing here with Python code. So with that, we can actually flip to, with that kind of foundational understanding of, the innermost loop of our logic of how we actually pack a bin, we can flip to the implementation with Ray. So one really important detail with Ray, just conceptually, the way it works is that we can take any regular Python and turn it into a Ray compatible actor and task by just simply adding decorators. So for example, if we have a function, right, just a simple Python function, we, in a class here, all we need to do to make it Ray compatible, so Ray can distribute it, is add these decorators. So to turn a function into a task, and again, a task is just like a remote action that's going to take place across your cluster. You just add the @ray.remote. So if you've used Python decorators before, very similar methodology for that. All it's saying is that, and what immediately comes after this decorator, I want to execute across a cluster or to execute remotely across a cluster. Then to call that, we use the .remote syntax and the .get syntax. So this is a little bit tricky to get the hang of when you're first getting started to make sure that your calls are not blocking. Like if you're using for loops, you don't want to put the .get inside of the for loop. You want to retrieve all of the results at the same time. But it's pretty simple to implement this for any type of arbitrary logic or function. The other major thing is an actor. So an actor is just a stateful class that's available across the Ray cluster. So we do the exact same thing, add .ray remote, and then we can call, any methods or properties of this class inside or using that same .remote syntax. So if we want to increment this stateful actor, we can do it like so. So it's a pretty simple syntax to convert a local Python function into a Ray compatible remote function or actor, which is a class. All right, so with that, we can actually see what this looks like converted into Ray. Before we get to the actual logic, I'll show a little bit of the setup steps. So to set up our Ray cluster, we have to initialize it on top of our Spark cluster. So in Databricks, Ray, it's called Ray on Spark. So the Spark cluster is initialized first. It's like any normal Databricks cluster. It has Spark pre-installed. You can see here I have 4 workers associated with this. So it's 1 driver and 4 worker nodes. To get Ray stood up, all I have to do is call an initialize function to initialize the Ray cluster on top of Spark. So there's a little bit of setup steps. Anything, this is a good tip for using Ray, any libraries that you want to be available for every worker on the cluster in Ray, you just put it into this runtime environment variable with a pip. This will just, install that library locally. And then we set up the Ray cluster. So this setup Ray cluster is part of the Ray library. And this is where there's a little bit of nuance of how to determine how much memory to give Spark, how much memory to give Ray, how many cores to give Spark versus Ray. If you're using GPUs, there's a little bit of nuance there as well. But in this case, we have a pretty simple cluster, pretty simple function. We're going to use some really base settings. And then all we have to do is call ray.init with that runtime environment that specifies our library, and it will initialize our Ray cluster. So if I zoom back out and scroll down, there's some helpful printouts. And one nice thing with this is you get a dedicated Ray dashboard. So if you've used the Spark dashboard, it's kind of analogous to this. The Spark UI lets you see what's happening in each task and in the execution plan. The Ray dashboard shows you what's happening with your actors and your tasks across your cluster. So to show you what this kind of looks like, let's make sure that this is still up. Here's my Ray dashboard. I see that I have one job that's currently running. You can see a little bit of the metadata about it. You can see the data, what was loaded across the Ray cluster. And then most importantly for our use case, we're going to come back to this. It shows us all of the tasks that have been executed across our cluster. So once we have that, it's pretty easy to get set up. And now you have any Ray function or actor or class that you call is going to be executed across all of the nodes of my cluster. So pretty easy to get set up on your Databricks cluster. So the next step is getting our data in. So first set of data we need is our containers, our inventory of what containers we actually have available. If you remember, we're trying to pick which container to send to which vendor who manufactures each item. So there's a couple different ways to do this, but we're going to set each of these containers up as a remote object. So you can think that this object is available kind of distributed across the cluster. So every worker, every task that we're going to call has access to it very quickly. We don't need to shuffle this chunk of data for every simulation or every trial that we run. It depends exactly how you're performing your optimization task. In our case, our object for the containers is small. It's just a few items. But if you have a very, very large, data frame like object, you might want to take a different approach. So there's some sample code here of how you would load it from a Spark table. So if you had a table called My Container Table, you could load it this way. For demonstration purposes, I am going to use just a list of dictionaries. And this is kind of our containers list. So you can see for each of these containers, we have an ID and the length in inches, the width, height in inches, the capacity, and then the bin volume. These are all kind of just random data, but they get bigger. Container 4 is much bigger than container 1. So you can see this holds 55,000 pounds, which would be a big container. And most importantly, we will put this containers object, right, this list of containers that we have accessible, into Ray remote storage using the ray.put. So again, this is going to take this Python variable and put it into essentially memory across our cluster, so it's accessible by each of the Ray actors. So it's a super important thing to keep in mind when working with Ray is if you're calling, not only if you're calling tasks, kind of how are you calling them and if they're blocking, but also if those tasks need access to data, where is that data located? You don't just want it on the driver or in cloud storage. You may want to put it in kind of the remote storage that Ray has kind of out of the box. So then we can build our bin packing logic. So I'll go through this part quickly because there's a little bit of details. We don't need to go through every single line. The first thing is just that function we looked at in the last notebook. So it's that same pack container where it's going to take a tuple of arguments and pack the bin. And all we've done is taken that basically exact same function and added the Ray remote decorator. So I won't go through this again. It's pretty much identical to the last notebook. And all we did is just add this Ray remote. The next thing we have to do is the outer loop. The next outer loop of this is we're going to calculate all the item permutations. So the way to think of this is if we have an item that the X dimension is 1, the Y dimension is 2, and the Z dimension is 3, we're going to calculate every permutation of those 3 dimensions. So if you do the math, that's 6 possible combinations. And so it'd be XYZ, XZY, XZY, XZXY, etc. And so you get to all 6. And this is really easy to implement with Python iter tools. So there's a little bit of more complex logic in here. One important thing we're doing is we're calling that pack container array function that we've defined above using the .remote method. Again, so this is basically like a lazy task that we're going to be scheduled to get executed, and then we'll retrieve the results from each of those functions. And the nice thing about this is you can put this in a simple for loop. The way that Ray is implemented, these are, you can use just normal Python to call or start the execution of these remote functions. And then at the very end, we will get the results. So again, this is an important implementation detail. We want to call the ray.get outside of the for loop so the results are retrieved asynchronously, right? If we did the ray.get here before appending it to this, in this case, we're appending like a reference to a result. If you know kind of how async in Python works, we're not actually appending the result, we're appending a reference to it. And then at the very end here, we're going to get all of those references back at the same time. So they can all be computed independently. Just, spin up these tasks through the for loop. And then at the very end, we'll get them all back at the same time. So it's an important implementation detail, can dramatically improve or decrease the speed of your Ray execution, depending on if your calls through Ray get are blocking or not. So really important detail, though, is we can call another Ray function or another Ray task from inside of another Ray task. So this is how we're building that kind of hierarchy or nested logic that we described at the top. And so the last thing is we're going to try one container for a specific item. So for example, in this case, we're going to determine the fill for the item in bin n, and then we're going to call this function n times for each item. So n is just the number of containers we had. In our simple sample data here, we just have 4 different container types. So this is really important. We want to get that container's remote reference or get that containers object from a remote reference on the cluster, right? So at the beginning, at the top of this notebook, I had some containers array, and I put that into kind of Ray remote object storage. At this part, I'm going to go retrieve it so that data is local to this task that's being executed. And then I'll do a very similar thing that we did before. I'll iterate through all of the bin arguments, and then I'll call the Ray, that next more inner layer of the Ray remote function, so that computes the item permutations. Very similar thing, very similar approach. We're just building that nested logic there. So now we have those 3 Ray remote functions, and we can actually apply this on each of our items. So first thing we'll do is we'll just do a really quick test on this, make sure that this works okay. There's a sample item input and Parquet file in here. This is just a couple of items, some random data that we can use to test to make sure that this works. One important thing that I'll call out is we're actually using Ray data to read in the file. So on Spark and on Databricks, there's several different ways to work with data and convert from Spark to Ray and Ray to Spark. We won't go into all the details here, but I encourage you to read up in the Ray data module. You can use Delta sharing tables. You can convert from a Spark data frame. You can have a query execute against a Databricks SQL warehouse. So there's many opportunities and options to convert from Spark to Ray and Ray to Spark. But in this case, we're just reading a single static file that we have loaded for demonstration purposes. So now that we have that items object loaded with Ray data, we'll just simply call a .map operation. So if you've worked with libraries like Hugging Face or, kind of think in like a map reduce mindset, the .map logic is pretty easy to reason about. We're basically saying for every item in this data object, apply some type of logic. The logic we're going to apply is that try container n written in Ray, right? So it's going to take everything in our data object and pass it to our outermost Ray function and execute from there. So you can see once we call this take one, this is kind of just making sure that the logic works for us. We're just going to kick off a bunch of Ray tasks. We won't go into the details at all, but you see that there's a map operation that gets kicked off. 8 active, 7 queued. You can see a little bit about the consumption or how the cluster is actually behaving as this task is going on. And at the end, since we just took one, we can see the printout at the back. So in this case, we just have our very first object in our loaded item data. We have a part number, again, just a random part number. It's some description, and then we have the length, height, width, and volume. So what this last part is what the array functions are returning to us. So these are the bin fills. So it's saying for container ID 1, we can't fit any inside of this container. So maybe this is not the best example. But if we come down to container number 4, we can actually fit 144 of this object in this orientation and 168 in this orientation. So our maximum fill rate is 67.1%. So this is just kind of a good validation that says this is a very large item. It's not going to fit in our smallest, our second smallest, or our third smallest container, but it will fit fine in our fourth container, and we can fill a bin about 2/3 full at an optimal setting. So that's good. So we've done it now for one item, but our real goal is to apply it to hundreds, thousands, tens of thousands of items at the same time. So we'll do the exact same logic and kind of put it into array pipeline. So it's very similar. If you've worked with Spark pipelines before, the logic is kind of similar. You'll chain all of these operations together. We'll just say array data, read parquet, our input file path. We'll apply that map operation just as we did before. So this is, again, the outermost loop of our array functions that calls the other array functions. And then we're just going to repartition it so that we get one file result, and then use array data to write back to an output file path. One other really nice thing when using array on Databricks is all of Unity Catalog is supported. So you can see that my output file path is a Unity Catalog volume. So if you've not worked with this before, this is just a mapping to cloud object storage, but it's fully governed under the kind of the UC governance model. So we're going to write out our final Parquet file to this volume as a Parquet file. You could also convert it to a Delta table, convert it back to a Spark data frame. But just for simplicity, we're just going to write out one output file just so it's really simple to understand what's going on. So when I kick this off, I ran it before. You can see that it's kicking off a lot of different tasks, and we can see the final time that it took was about 80 seconds. So you can do some back of the envelope math based on this example of how long it would have taken to run if we had done it sequentially, right? Like I think there's about 50 items in the sample data frame here times 4 bins times 6 orientations, and figure out, how much faster Ray is than the single node kind of nested for loop approach. But, this is just a trivial data set. For the actual customer examples, it was, I think 40x faster. So just to show you what's actually happening on the Ray cluster, we can see it in the Ray UI. So the Ray dashboard, oh no, it failed on me. It looks like my cluster crashed. Well, I'll skip that part. But you can actually see the exact execution logic. And for each of the item permutations, each of the calls to the innermost function of Ray, we're going to have very detailed metrics of how long did it take, how much memory did it consume, how much data was passed. So you get super granular views into the actual execution logic. And the Ray UI will map the logic of the function. So if you have functions or tasks calling other tasks in Ray, you'll actually see that hierarchy in the Ray dashboard. So sorry that the Ray dashboard wasn't available anymore, but we'll move on. I kind of pre-ran some of this code. So yeah, I guess 30 items, 4 bins, 6 starting orientations, so 720 trials. The other nice thing you can do, because it's all in Databricks, oh, this didn't run properly, is you can actually start to read this back with Spark. So some things are just much easier to do for analysis purposes in Spark or SQL. And because this is a UC governed asset, we can just load it back with Spark. And some things are just, like kind of analysis processes are just easier with kind of the Spark syntax rather than Ray. So this did not, this command failed as well. So we'll skip that. But the main takeaway from this is we can take any type of single node scientific computing logic. In this case, we're packing bins, but traveling salesmen, simulations, anything that requires, you know, many things to be kicked off at the same time, or if it's kind of logically parallelizable, we can wrap that really easily, convert a code base using the array decorators, and then execute it on a Databricks cluster. And then you also get the governance benefits of Unity Catalog, the governed cluster kind of format that Databricks provides, and it's pretty easy to get started and use. So that kind of brings us to the end of the overview of this blog. If you are interested, again, the name of the Databricks Solution Accelerator is Scientific Computing Array on Spark, and you can check that out. Feel free to let us know if you run into any issues or questions using Ray, and excited to see what you come up with.